This story began some years ago when I was pondering a question concerning binary operations, operations that take two inputs and produce one output. The two basic binary operations in math are addition and multiplication, and together these satisfy the distributive property, namely a times x plus y equals ax plus ay, and a plus b times x equals ax plus bx. I wondered whether it was possible to define a third operation that distributes over multiplication, just as multiplication distributes over addition. Specifically, if one denotes this hypothetical operation with a star, the goal is to define it such that these two properties hold. An obvious first candidate is exponentiation, since there's a way in which the relationship between exponentiation and multiplication is the same as that between multiplication and addition. Namely, when one of the inputs is a natural number, then multiplication is the same as repeated addition, and exponentiation is repeated multiplication. And exponentiation does satisfy this property, since ab to the x equals a to the x times b to the x, but it doesn't satisfy the other property, since a to the xy is not usually equal to a to the x times a to the y. I wanted an operation that satisfied both distributive properties. If you'd like, you can pause the video and try to find a solution yourself. At the time, I couldn't think of a solution, and I forgot about the problem for a while. But when I returned to it a few months later, I realized that the solution lies with that all-powerful function, the exponential function. This is often denoted as e to the x, but I'm going to write it as exp of x instead. This function has two crucial properties. First, exp of x plus y equals exp of x times exp of y, and second, it creates a one-to-one correspondence between real numbers and positive numbers. Every positive number y has a unique number x such that exp of x equals y, and this is called the natural logarithm of y, or log of y. Mathematicians have specific terminology for properties like these. A function that converts one operation into another is called a homomorphism. So property 1 could be restated as exp is a homomorphism from addition to multiplication. And a function that creates a one-to-one correspondence is called a bijection. So property 2 could be stated as exp is a bijection from real numbers to positive numbers. Lastly, a bijective homomorphism is called an isomorphism. So these two properties taken together say that exp is an isomorphism from addition of real numbers to multiplication of positive numbers. Whenever you have an isomorphism between two operations, they're called isomorphic. And isomorphic operations have essentially the same structure because you can go back and forth between them using the isomorphisms while preserving all of their properties. In our case, you can go back and forth between addition of real numbers and multiplication of positive numbers using exp and log. So any property that holds for one operation must also hold for the other. One of these operations, addition, has another operation that distributes over it, namely multiplication. And this means that multiplication of positive numbers, being isomorphic to addition, must also have an operation that distributes over it. Just as exp converts addition into multiplication of positive numbers, it will convert multiplication into this new operation which I'll call star. We can get a formula for star by replacing x and y with log of x and log of y. The exp and log cancel out since they're inverses, and we get that x star y equals exp of log of x times log of y. Star does indeed distribute over multiplication. A direct proof of this is on the screen right now. And star is isomorphic to multiplication by construction, so it shares all of the properties of multiplication. Multiplication is commutative and associative, therefore star is commutative and associative. And just as anything times 0 is 0, anything star exp of 0 is exp of 0. And just as x times 1 equals x star exp of 1 equals x. And just as every non-zero number has a multiplicative inverse, every positive number except 1 has a star inverse. Lastly, just as every positive number has a square root, every number x greater than 1 has a number y such that y star y equals x. You can find y by this formula. If you want to see what the star operation looks like on a graph, here is a graph of x star a with a varying over time. You can see that when a is 1 over e, the function is 1 over x. When a is 1, the function is just 1. When a is e, it's x, and when a is e squared, it's x squared. Why is this? Well, in calculus, it's common to define exponentiation as x to the y equals x above log of x times y. If you compare this definition to the definition of star, you can see that x star a is equal to x to the log of a. So if a equals e to the z, then x star a equals x to the z. As of yet, we have three binary operations: the standard operations of addition and multiplication, and this new star operation. The first two are defined for all numbers, but the last is only defined for positive numbers. And these operations form a kind of chain where multiplication distributes over addition, and star distributes over multiplication. It turns out that we can extend this chain into an infinite sequence of binary operations, with each distributing over the one before it. I'll call the next operation in this sequence diamond. Just as x star y is x above log of x times log of y, x diamond y is defined as x above log of x star log of y, which you can expand to x above log of x times log of y. This is defined for all numbers greater than 1, distributes over star, and just like star, inherits all the properties of multiplication. For example, x diamond e equals e, and x diamond e to the e equals x, so e acts like 0 and e to the e acts like 1. Before we continue, it's a good idea to systematically name these operations. I'll use a dot symbol like I've been using for multiplication, but with a subscript added. So dot 0 means multiplication, dot 1 is the same as star, dot 2 is diamond, and so on. And to avoid having to write log so many times in a row, I'll use superscripts for repeated application. So log 2 of x means log of x, log 3 of x means log of x, and so on. And I'll do the same with exp. Here are the definitions of star and diamond written in this new notation. Now we can define the rest of the operations all at once. The dot n operation takes two numbers x and y, applies log n times, multiplies the results, and then applies exp n times. Whenever you define a new operation, it's important to know what its domain is, what inputs it accepts. In the case of dot n, the only thing that could restrict the domain is this repeated application of log. Because exp and multiplication both have unrestricted domains, they can work with any real numbers, so we don't need to worry about them. So the domain of dot n is the same as the domain of log n. Log 0 does nothing with its input, it applies log 0 times, so its domain is the entire number line. To work out the rest, we can use the fact that log and exp are inverses, which implies that the domain of log n is the same as the range of exp(n), the set of possible outputs of exp(n). If we apply exp once, the outputs are all numbers greater than 0. If we apply it again, 0 gets mapped to 1, and since exp is an increasing function, anything greater than 0 will map to something greater than 1, so the range of exp2 consists of all numbers greater than 1. Likewise, the range of exp3 is all numbers greater than exp of 1, the range of exp4 is all numbers greater than exp of 1 or exp2 of 1, and so on. If we write these lower bounds using the e notation, we find they're equal to e, e to the e, e to the e to the e, and so on. As you might imagine, this sequence grows very, very quickly. E to the e is approximately 4 million, and the next value in the sequence is too large to represent on a computer, but I worked out that it's about 1.65 million digits long to the left of the decimal point. This means that the dot 6 operation only works on numbers with more than 1.65 million digits. Not very practical, I must admit. So we've worked out the domains of all the dot n operations. I'll write these as kn, so k0 is the entire number line, k1 is the set of positive numbers, and so on. And I'm going to introduce another notation as well. Just as we defined x dot ny as exp(n) of log n of x times log n of y, I'm going to define x plus ny as exp(n) of log n of x plus log n of y. This doesn't really add anything new because plus n is just a more restricted version of dot n minus 1. For example, plus 1 is the same as multiplication, but only works on positive numbers. Nevertheless, this can be a useful notation to have. You can think of kn as a smaller copy of the real numbers hidden within the real numbers. It has two operations defined on it, plus n and dot n, and these operations obey all the properties of normal addition and multiplication, but with 0 replaced by xben of 0 and 1 replaced by xben of 1. And these smaller copies of the real numbers are related to each other in two ways. First of all, the dot operation of one copy is the same as the plus operation of the next, and second of all, you can go from kn to kn plus 1 using exp, and go the other way using log, and these two functions are isomorphisms. So plus n is a more restricted version of dot n minus 1, but this is not true for plus 0 because there's no such thing as dot negative 1, and if there were, its domain k negative 1 would have to be larger than the real numbers. But we shouldn't let that stop us. The rest of this video will be devoted to defining k negative 1 as well as kn for all negative integers n, resulting in a new number system which I call the exponential numbers. Since log maps each kn to kn minus 1, it should map k0 to k negative 1. This means that k negative 1 will contain the real numbers as well as log of 0 and a logarithm for each negative number. For now, I'll draw this set as two lines with a point in the middle. The top line represents the real numbers, the central point is log of 0, and the bottom line consists of logs of negative numbers with log of minus x placed directly below log of x. For example, 0 is log of 1, so the point below 0 is log of minus 1. 1 is log of e, so the point below 1 is log of minus e. To help you visualize how this extended logarithm works, I'll draw a red dot here, call this number x, and draw a blue dot at the point log of x. As x approaches 0, its logarithm shoots off to the left. At exactly 0, its logarithm is the center point, and as it decreases further, the logarithm shoots in from the left, but now on the bottom line. Because of this behavior, I think it's accurate to call this center point minus infinity, and to say that these lower points are less than minus infinity. I'll introduce a new notation for these numbers. I'll denote the point directly across from x as squiggle x, so log of minus 1 can also be referred to as squiggle 0. Applying the squiggle function is the same as reflecting across this horizontal line. An explicit definition is given by squiggle x equals log of minus exp of x. To see how we can extend addition to this number system, we'll first look at how multiplication extends from the positive numbers to the real numbers. In other words, how can we define real number multiplication in terms of positive number multiplication? Well, if both of the inputs happen to be positive, we simply multiply them. If exactly one of the inputs is negative, we negate it to get two positive numbers, then multiply and then negate the result. If both are negative, we negate both of them and multiply, but we don't negate the result because negative times negative is positive. The only remaining case is where one or both of the inputs are 0, and in this case we just return 0. Now we'll repeat this construction, but instead of extending multiplication from positive numbers to reals, we'll extend addition from k0 to k negative 1. All we need to do is replace multiplication with addition, 0 with minus infinity, and minus with squiggle. For example, if you want to add these two numbers, you apply squiggle to make them both real, then add them together and then squiggle the result. This is the best way to visualize the extended addition operation, but there's a simpler way to define it. If you replace squiggle x with log of minus exp of x, replace the remaining occurrences of x with log of exp of x, do likewise with y, and then expand the remaining squiggles, you get these horrific expressions. If we simplify them using the rules for log and exp, the minuses all cancel out, and in each case we're left with log of exp of x times exp of y. The case where one of the inputs is minus infinity also fits this formula, because if we plug in minus infinity, we get log of 0 times something, which is minus infinity. Therefore, our extended addition operation can be defined with this one formula. If you replace exp with log negative 1 and log with exp negative 1, and recall how we defined all those dot operations, you can see that what I've been calling extended addition could also be called dot negative 1. We can define plus negative 1 in a similar fashion. So we've succeeded in extending this tower of operations in the negative direction. But we have the same problem now as we had before. Unlike all the other plus operations, plus -1 has no generalization. And the problem runs deeper than that. K-1 is isomorphic to K0 because one can go back and forth between them using exp and log while preserving the structure of the dot and plus operations. K-1 might seem like a crazy new number system containing values less than -infinity, but its structure is the same as that of the real numbers. It's the real numbers in disguise. K-1 is best thought of not as a new number system, but as a relabeling or alternative presentation of the reals. Nevertheless, this alternative presentation can give us insight into how we can extend things further. Once we've defined .n and plus n for all integers n, we really will have a new number system. To make this easier, I'm going to change how I depict K-1. Instead of putting log of minus x directly below log of x, I'm going to put it below minus x. And similarly, log of 0 will go directly below 0. This arrangement is less symmetric, but it's more obvious now how we're extending K0 to K-1. We're just adding logs of non-positive numbers, and we can keep going. So now we have a line at the top representing the real numbers, and infinitely many half lines below it representing logs of non-positive numbers, logs of those numbers, and so on. I'll call this whole set E, and call its elements exponential numbers. Every exponential number has a logarithm, which is itself an exponential number. This property makes E unique among all the sets we've seen so far. We can now define Kn for all integers n. K0 is the top line, K-1 is the top 2 lines, K-2 is the top 3 lines, K-3 is the top 4 lines, and so on. And the definitions of plus n and dot n now make sense for all negative indices. For example, .-3 takes two inputs, x and y, applies exp 3 times to each of them, multiplies the results, and then applies log 3 times. The domain of this operation is K-3 because the formula only works if applying exp 3 times gets you to the real numbers, so the input has to be somewhere in the top 4 lines. There's an easier way to visualize these operations. First, we extend each of these half lines into a full line. Each point is the log of the point above it, so this is the log of this. But this is also the log of the red point, so these 2 points are equivalent. They represent the same exponential number. There's no longer a one-to-one correspondence between numbers and points. In fact, each number is represented by infinitely many points. To give you an idea of which points are equivalent, I'll draw these guidelines. Earlier I said that K-2 consists of the top 3 lines, but now we can think of the third line on its own as K-2 since all of the points above this line have equivalent points within it. So each of these lines corresponds to Kn for some non-positive n. We can extend this to positive n as well by drawing K1 on its own line above the real numbers, and so on. To be clear, we aren't adding any new values by doing this, but it makes the presentation more symmetrical. So here's how to visualize the dot and plus operations. Say we want to apply plus -2 to these two values, x and y. Each is represented by several points on the screen. We look at the points which are on the K-2 line and add them as if it were the real number line. The result is x plus -2y. For another example, suppose we want to apply .2 to these two values. We look at the representations on the K2 line and then multiply them as if this were the real number line. So to summarize, we've constructed this set E by extending the real numbers with logs of non-positive numbers, logs of those values, and so on. E contains a subset Kn for each integer n, and these subsets form an infinite descending chain with Kn plus 1 contained inside Kn. K0 is the real number line we started with, and Kn is defined as the set xben of x for all real numbers x. For example, K-2 is the set of logs of real numbers, since exp-2 is the same as log 2. Each Kn has its own versions of addition and multiplication, denoted plus n and dot n, and these are defined as shown. Plus n is the same as dot n minus 1 when both are defined, and this means that .n distributes over .n minus 1. In other words, we have a chain of binary operations, with each distributing over the one before it, and this chain extends infinitely in both directions. I'll end this video with two exercises for the viewer. First, there is a natural bijection between the exponential numbers in the reals, mapping 0 to 0, 1 to 1, e to 2, log of 0 to minus 1, and in general mapping xben of 0 to n for all integers n. Find this bijection. Second, show how e can be defined as a colimit. Leave your answers in the comments, and of course subscribe to my channel. I'll be posting more videos like this in the future.